In this video, we're going to talk about non-symmetrical distributions. So we've talked a little bit about the uniform distribution, which is uniform across the entire range. We've talked about the normal distribution, which is going to be symmetric, but very clearly centered around kind of a center point, which could be anywhere, but the idea is there exists some mean that most of the data kind of congregates around, with the data kind of following around it and getting less likely to appear farther and farther away. However, as we mentioned before, data can come in all shapes, and we have no issue with that. Data can be non-symmetrical. So if we're looking at a non-symmetrical distribution, we can still analyze it, we can still talk about it. In this course, we're not going to really spend a lot of time, though, talking about different specific names for non-symmetrical distributions, because there are many. We will see like the F distribution later, we will see the chi-square distribution later. But for now, we're just talking about the fact that data can fall in different shapes. And so we should know terms about skew, for example, remembering that right skew means that most of the data is on the left, or I don't know, you might be looking at the wrong side of the screen. So I think it's, for you, most of the data might be on the left, but kind of skews off to the right side, and then most of the data might be, let's see, left skewed, meaning that it's mostly concentrated on the right but skews off to the left. Beyond that, we won't really use any more terms to describe non-symmetric distributions, though. Now, if we were taking a higher level course, we would kind of name these distributions, and we would talk about the distribution function that represents a particular curve, and we could use calculus to find the area under the curve for any given range, for any given function. In this class, we'll just kind of do it more in terms of using, say, a table like we do here, or just kind of making observations from, say, a histogram like shown here. So an example of a discrete random variable that would probably be non-symmetric would be maybe how many children different married or partnered couples have. So most couples are probably going to have between, say, 0 and 2 children. 0, 1, and 2 are going to be very common numbers. However, we still obviously see couples with 3 and 4 and 5 children. It's just that it's going to get less and less likely the farther away we get. So there is going to be kind of an initial peak, probably around 1 or 2, and then that number is going to noticeably kind of drop off. So it'll be kind of non-symmetrical later. So skewed variables are really common to see when there's a very clear lower floor or upper ceiling for a variable. So if a variable can't be below 0, but there's data points around 0, that's a good candidate for kind of a right skewed variable. So a lot of like financial variables can often be right skewed for that reason. And if there happens to be an upper ceiling for a particular variable, so like I think professor ratings is probably a good example, where professor ratings are going to be between 1 and 5, and most students do typically give around a 4. I think the average student evaluation ratings are usually around 4, maybe just a little bit above 4. So typically you see most professors with ratings kind of in that 4, high 3 range, and then you see it kind of get lower and lower, or less likely for professors to get lower and lower scores. So here we have an example with a data table this time, representing the weights of cats that have been up for adoption at a local shelter over the last 5 years. So this is a variable that's very important to me. I love cats, so I like analyzing data involving cats. And so our first question here is, what is the probability that a randomly chosen cat that was up for adoption in this time period weighed at least 9 pounds? So I'm going to look here, and I'm going to notice that data involving cats above 9 pounds is going to be this sector of the table. And it looks like 10, 20, 28% of the cats are in this particular range. So I'm going to say, I'll say 0.10 plus 0.10 plus 0.08 is going to be 0.28. And I guess I could have also just added that up as percentages as well, right? 10% plus 10% plus 8%. I guess it's more typical when you're doing mathematical calculations with percentages to use them as decimals, but either way is technically fine, I guess. Is this distribution uniformly distributed, normally distributed, or non-symmetrically distributed? And so I would look at this and I would say that this data appears to be rather non-symmetric. And speaking of cats, my cat is actually clawing at the door right now. So maybe my cat should make a very brief brief hello here if she's still there. 1 second. She just heard me talking about cats and she really wanted to get in the video. So here's your big chance to see Truffle. She's very excited about this. Okay. Oops. You wanna go up there? It's fine with me. Okay, good. So this distribution appears to be pretty non-symmetric to me because, and one thing that I'm going to notice here is that most of our data appears to be on the lower end, right? So most of our data is around 1 to 2.9 or 3 to 4.9, and the higher we get, the fewer cats that we see. And that's probably because at shelters, most of the cats are typically going to be kittens. There's always going to be some adult cats that just don't really get adopted. But there's always going to be a lot of kittens at shelters, and those will get adopted fairly quickly, and there will always be a few cats that just don't get adopted, unfortunately. So I would say this is probably non-symmetric. And one other check that I can kind of do here, right, is that I can kind of plot the data myself here, right? So 27%, 19%, 14%, 12%, 10%, 10%, and 8%. So I can kind of see that as well if I just want to check that in a graph there. All right, approximate the median from this table. Do you think the mean is approximately equal to the median, less than the median, or greater than the median? So if we're going to approximate the median, remember that the median is going to be the 50th percentile. So it's going to be the value such that half the data is below and half the data is above. So if I look at this table here, I'm going to try to find where do I meet 50%. So if I start from the beginning here, if I start from the lower end, how far do I get before I hit the 50th percentile? And it looks like I'm going to have to get somewhere into this row, right? Because 27 plus 19 is going to be 46, right? So that doesn't quite give me to 50%. So I'm going to reach 50% somewhere in this 5 to 6.9 range. I don't know exactly where it is, but I know it should be in that range. So I'm just going to say between 5 and 6.9. And if I had to do an educated guess, since I'm really close to 50% coming in, right? So I'm at 46% here, and then when I get here, I'm at 60%. So it's probably a little bit closer to this side than this side. So I'm going to say it's probably about 5.5 pounds if I had to put a best guess. And that's my logic for doing that, is because I do think it's probably closer to the lower end than the higher end based on how close I am walking in that range. Now, the second part of this question, do you think the mean is approximately equal to the median, less than the median, or greater than the median? And this goes back to chapter 1 where we talked about the mean is more responsive to kind of these more extreme values, whereas the median is going to find the 50th percentile. So if I have a skewed distribution, that means that the mean here is going to get pulled up, whereas the median is going to kind of find that 50th percentile, that center data point. So for that reason, the mean is very likely higher than the median. And I say very likely because you can have slightly skewed distributions where that's not true, depending on exactly how the data is distributed. But if there is a pretty clear skew in the data, then this is pretty much always going to be the case. If it's a slight skew, it just depends. It depends on exactly how it's going to be distributed. But But if there's a clear skew, then this is really always going to be the case. The mean will be likely higher than the median. Since this is right skewed, so the mean will be pulled higher than the median in that case.